Yesterday we started talking about chemical reactions. We mentioned what a chemical reaction is. So that's where something new is formed. You have a new compound forming, and in most cases it is not reversible. So you can't just go back and get your reactants again. Right, then there are factors which affect the speed or the rate of a chemical reaction, and those are concentration of a solution, pressure of a gas, surface area of a solid, temperature, and catalyst. So we've talked about the first three, right? And we've talked about them with regards to the collision theory. So the particles of the reactant should collide, and if they have sufficient energy, which is known as the activation energy for the reaction to occur, then those collisions can result in successful collisions and lead to the formation of products. So we talked about how surface area allows more area, of the reactants to be available for the reaction, and then the concentration just increases the number of particles available, and so that would increase the collisions, and then hopefully successful collisions, thereby increasing the rate of reaction. And right, pressure is also increasing the number of particles within that space, and so you got more particles, or in fact not more particles, right, the same number of particles in a lesser volume. That would increase the number of collisions taking place, hopefully increasing the number of successful collisions, thereby increasing the rate of the reaction. Today we'll continue from there and talk about how temperature affects the rate of reaction.
Okay.
And so for this, right, the concept is going back to the kinetic particle model, and the effects of temperature, and how changes of state take place, but not change of state in this case. And so basically when you raise temperature, you are increasing the energy of the particles, and when they are increased, they're moving about faster. When they're moving about faster, you have more collisions, more successful collisions, and therefore an overall increase in the rate of the reaction. Right, so that is the concept behind temperature affecting the rate of reaction. Now, obviously, if you decrease the temperature, you will slow down the reaction, right? And so that is why you keep food in a refrigerator, right? Or sometimes even the freezer. And the
Yeah.
reason, right, the reason for that is if you leave food out, you've got microorganisms on it. It will naturally decay. It will naturally, spoil. And so the low temperature of the refrigerator slows down that process. And so as compared to leaving it out in the open where food might spoil overnight or in a matter of hours, you'd have it last between a few more hours to a couple of days, right? A few days. And so you're slowing down all the chemical reactions that lead to decay of food. Now, okay, that's on a side. Now, how can we test the effects of uh, temperature? And so we repeat the sodium thiosulfate experiment, right? And this time, instead of uh, changing the concentration of sodium thiosulfate, what we do is we carry it out at different temperatures. Right, all the way from, let's say, uh, 25 degrees till 60 degrees centigrade, right? And as you would expect, the hypothesis would be that, right, so the prediction would be that the reaction would occur much faster at higher temperatures.
Yeah. Okay.
And so without using, proper values, so you've got temperature over here in degrees centigrade, and you've got the time taken for, the cross to disappear in seconds, so time per second. And again, what you would notice is as you increase the temperature, right, the time taken decreases, right? Now again, you can use the thing with the rate, right? So you can do 1 upon time per second, and then when you plot it, right, so the rate, you get a higher rate for higher temperatures. Okay, and you get a linear graph. So that is what you expect, and that is what's happening. And the reason for that is, right, you are increasing the kinetic energy of the particles. Clear?
Yeah.
So, right, simple, straightforward. Haran, all clear?
Yeah.
Okay. Then we have catalysts. So what is a catalyst? Right? It is a substance which can alter the rate of a reaction without being chemically changed itself. Right? And we'll see, right? So the focus over here is not being chemically changed. It can be physically changed in some way, right? But not chemically changed, right? So it's not going to react. It's not going to take part in any of the reactions that are occurring for which it is being used as a catalyst, right? And so what a catalyst does is that it provides an alternate pathway for the reaction. So it increases the rate of the reaction by providing an alternate pathway, reaction path, which has a lower activation energy. So basically what's happening is, right, you have the reaction progression, and if, for example, you had your reactants here and it had like a bump of activation energy and then coming down to the products. What a catalyst would do is it would greatly reduce the activation energy required. All right, so the energy difference, the enthalpy difference between reactant products, right? The negative delta H is going to, that's not going to change, right? So it's not affecting the enthalpy. Keep that in mind. What it's affecting, right, is the activation energy. So instead of having all of that, it now has only this. So lower activation energy, right? And this is the same. The enthalpy change does not, you know, is not affected.
Yeah.
Okay. And right, what I mean happens basically is that the surface of the catalyst plays a role, and it provides, you know, a place for the particles of the reactant and the product to come into close proximity, and so it makes it easier for them to react as opposed to moving around the entire container where they are. Okay,
Yeah.
so that's what happens. So the examples I've given, right? And so the in fact, before going into the example, uh, just to clarify that the catalyst is not increasing the number of successful collisions, right? So I should rephrase. The catalyst is not increasing the number of collisions between the reactant particles, but it causes more of the collisions to become successful collisions. So catalysts do not increase number of collisions, right? So it's not like temperature or pressure or something, but right, cause more collisions to be successful collisions, which basically means that they're reacting, right? And that will increase the rate of the reaction. And so more particles, right, the activation energy is lowered. And so on collision, more of the reactant particles will form products. Right, at a given temperature. So in an industrial process, really, right, it's all a balance of how much catalyst are using, and right, 90%, as they mentioned, industrial processes use catalyst. So the example that they've given, right, let's get to the example, is the decomposition of a compound called hydrogen peroxide. So the example is decomposition of hydrogen peroxide. And so what hydrogen peroxide is right, you've got hydrogen peroxide and it decomposes into water and oxygen. And so you got H2O2 as, right, aqueous, giving you H2O plus O2. So that's a liquid and this is a gas. You want to try and balance this?
Well, H2 is balanced. Uh,
We need three oxygens.
You've got
Like there are two oxygens.
two oxygens on the reactant side, three on the product side.
Uh, we can add three on the product side.
Where?
On the product side.
Like, so 3O2 over here.
Oh, sorry, on the reactant side, I guess. Yeah.
So this.
yeah,
Yeah.
So that's going to give me 6 hydrogens and 6 oxygens.
So we can add two on the. Oh, sorry, no.
Uh-huh.
mm, actually remove the 3.
Uh-huh.
Uh, 3 on the reactant side.
Okay, I'll tell you. There's no 3.
2.
Two.
Is there a 2?
Oh, like two on the two for hydrogen on the reactant side. Oh, on the product side. Reactant.
So now you've got 4 hydrogens here, 4 hydrogens here. You've got 4 oxygens here, 2 and 2, that makes 4. So it is balanced.
Yeah.
Okay. So that is how the decomposition of hydrogen peroxide occurs, right? And it happens on its own. So at room temperature, it's very slow. Okay. So
Yeah.
at room temperature, which is 25 degrees, so right, not the temperature of the room you are in, but the scientific standard for room temperature. So at room temperature, right, the decomposition is very slow. So what you can do is you can add a catalyst of manganese 4. Manganese 4, right? Manganese 4 oxide, in fact, right? As a powder. Now remember, even for catalysts, right? If it's a powder, that means it's got more surface area to interact with the reactants, and that's as opposed to putting in a chunk of manganese 4 oxide. All right. And so now what you see is that the rate is, really increased, and oxygen is produced rapidly. And so you can measure the effect of adding a catalyst by measuring the volume of oxygen gas produced over time. So you can follow the rate of reaction by measuring volume of O2 produced.
Okay.
right? And so as mentioned, you can speed up the reaction even more. By one, increasing the amount of catalyst, and secondly, increasing the surface area of the catalyst, right? So the best thing you can do is use it in powder form, as I mentioned earlier. Right? And so, right, the manganese 4 oxide is not affected chemically, but in this case, it is affected physically in the sense not that state changes, right? But uh, when it was used as a powder at the end of the reaction, it was, when it was filtered out, it was found as an even finer powder. So first of all, right, the manganese 4 oxide can be filtered and reused. Okay, and so what are observations? A small amount of catalyst will produce a large change. Then catalysts are specific to a particular chemical reaction. So it's not like you can throw in anything in any reaction and expect it to work. So catalysts need to be chosen with care.
Yeah. Okay.
And lastly, as I mentioned, that they remain unchanged chemically, but they can be affected physically. So the manganese 4 oxide is not going to react and make a hydroxide or any other salt. It's going to stay as an oxide. Right, so in this case, the manganese 4 oxide turned to a finer powder. It was used as a powder anyway, and then at the end of the experiment it was a finer powder. So in the book they've given you a graph of amount of the catalyst used and the rate of reaction. So as you would expect, the more the catalyst was, the faster the rate of the reaction was. And then they also mention some processes where catalysts are used and which catalyst is used in those. And so we'll actually study those, right? Two of them are the Haber process for the manufacture of ammonia, which uses iron as a catalyst, and the other is the manufacture of sulfuric acid, which is called the contact process, and it uses vanadium 5 oxide, right? So we'll study both of those in this chapter. The other two will come later on, which is the oxidation of ammonia to give nitric acid, and then the hydrogenation of unsaturated oils to form fats, right? And that will come later on when we talk about organic chemistry. Now, just one last thing about this before we talk about enzymes, which are biological catalysts, and is that in reactions that are involving gases, so in gaseous reactions, right? If there are impurities present on the surface of the catalyst, then obviously it will not be acting efficiently, and that's because I told you that the surface of the catalyst plays an important role in lowering the activation energy and speeding up the reaction. So if impurities, right, and impurities could be dirt or anything else, are present on the surface of catalyst, it will not work efficiently. So it won't give you the speed increase in the rate of reaction as you would expect. And in this case, the catalyst is said to be poisoned. So that's the term they use for it. So obviously, even for the catalyst, what you want is you want to have a pure, substance. On that note, right, we're going to talk about enzymes, which are also catalysts, but in biological systems, so living systems. So they're proteins produced in living cells, are biological catalysts, right? They are proteins produced in living cells, and I do believe the mention of amino acids and proteins will come up later on in organic chemistry.
Yeah.
And they speed up, in fact, almost all reactions taking place inside living cells are catalyzed by enzymes.
Yeah.
And so they speed up reactions in, right, living cells. And just like, you can't use any catalyst for any reaction, these guys are also very specific. And so you've got different enzymes for different reactions. So each chemical reaction in a living system has a specific enzyme. To catalyze it. And the reason for that is similar to what we saw in hydrogen peroxide, right? If you leave reactions in living systems to happen on their own, they might, but they would just take so long that by the time they happen, the organism would be dead much before. And so to sustain life, you need those reactions to happen very quickly. And that's why you need catalysts. So instead of you drinking, nickel or manganese for oxide or iron or platinum or any of those other right things which are, if you do consume those directly, they are harmful and toxic and deadly and fatal and all of those things. You've got these biological catalysts, so they are molecules that are well suited to the living system, right? And they do a great job in speeding everything up. Okay. Now, right, that's all about uh,
Catalyst.
catalysts.
Yeah. That's all.
No, that's not all. Let's talk about reversible reaction.
Okay.
Reversible reactions and equilibria.
Yeah.
Yeah. Any questions, by the way?
No, not from my side.
Karam, all good?
Yeah.
Okay. As mentioned earlier on, there are certain reactions that are reversible, right? So we know about reactions that are not reversible. Most of them are not reversible, right? For example, the production of carbon dioxide when carbon reacts with oxygen to give carbon dioxide, you cannot go back on that, right? But in some cases, right, chemical reactions are ones in which reactants can form products, and then those products can go back to forming reactants in the reverse, right? So reactants, products, and as I mentioned, the symbol for reversible reactions are these half arrows going both ways, right?
Yeah.
And so what happens in a reversible reaction is, right, you end up with sort of a mix of reactant and products, as opposed to a regular reaction where the it only goes one way. So the reactants can react and form products, it can't go the other way. In this case, you have a mix of reactants and products, right? Okay. And so the proportion, but you can change the conditions of the reactions to make it move one way or the other. So the proportions can change or be altered uh, depending on the reaction condition. So we will come across reversible reactions when we talk about the manufacture of ammonia and sulfuric acid industrially. But over here, we're just going to talk about something very simple, which we have come across earlier. And I think I'll end the class just a bit earlier today after I complete this particular bit. And so what we're looking at is, kind of a chemical reaction. If you remember when we were talking about acid, bases, and salts earlier, chapter 8, I believe it was,
Yeah.
and we talked about copper to sulfate and water of hydration,
Yeah.
right?
Yeah.
Water of crystallization, sorry. And so when crystals are formed in certain compounds, they trap water as well, and that affects their properties and their appearance. And we, in fact, came across a reversible reaction back then, right? So we talked about copper 2 sulfate and the fact that its crystals can be hydrated or anhydrous. So, right, copper 2 sulfate right, can be either hydrated, in which case it appears blue, or it could be anhydrous, meaning you remove the water, in which case it appears to be white. And so how is this going to, affect, how is this going to be an example for a reversible reaction? So what you can do is you can take hydrated copper 2 sulfate and going this way, right, you can heat it and you can get anhydrous copper 2 sulfate. Or you can go the other way by adding water. All right, so again, the reaction conditions, right?
Yeah.
And so what you will, right, plus water. Why am I saying plus water? Because when you're heating it, the water is evaporating. So this guy is evaporates.
Yeah.
Okay.
Okay.
So you're noticing a color change going from blue. That is how you know it happens.
Mm.
Going from blue to white. Now, why is this a chemical reaction? It's a chemical reaction because, as we saw earlier, right, the water of crystallization is incorporated into the crystal. So it becomes part of the crystal. So it affects its properties and its appearance, right? So, right, it sort of qualifies for a chemical reaction. And so there's an image in the book showing a test tube with copper 2 sulfate in it, which is like a white powder, and they add some water into it. And so the top layer, which comes into contact with water, turns blue. Right? Pretty simple, pretty straightforward. Another similar example is cobalt 2 chloride. So it's pretty much the same thing as this, right? You got hydrated and anhydrous copper 2, cobalt 2 chloride. So cobalt 2 chloride can be similarly either hydrated, right, which gives you a pink solid, or anhydrous, which will give you a blue solid. And so for this reversible reaction, we can write it this way as well. You've got anhydrous cobalt 2 chloride plus water. And so going this way, you're adding water. And you are getting hydrated cobalt 2 chloride. And obviously going the other way, you heat it and you get the anhydrous. And so this guy over here is blue. And this guy over here is pink. All right.
Yes.
Now, I'll stop here. And so what we are left with is talking about ammonia, right? The industrial production of ammonia,
Yeah.
And along with that, we will talk about equilibrium, right? So what equilibrium is, what it means, and right how it is affected
Everything
by,
about that, basically.
huh?
Everything about that.
Well, yes, right. So they've mentioned equilibrium in the middle of talking about ammonia. So
Okay.
right, I'll try to talk about equilibrium first, and then we'll talk about the formation of industrial formation of ammonia, and then the contact process for the manufacture of sulfuric acid. Anyway, I'll stop here. Are there any questions?
No.
Okay, so have a good weekend. I'll see you guys next time.
See you guys soon. Yeah, that's it.
Allah.